welcome to Ako Math Musings channel. My name is Alexander. Today we continue shaking our mental model of numbers, and today's topic is dual decimals. We considered in the previous two videos the two operations of addition, plus and what we call dual plus. We applied it to common fractions, and today we will consider decimal fractions and how we can introduce decimal fraction notation for dual plus operation. So the plan is as follows. First we will consider how decimals and fractions are connected, and then we will go to the topic of this video. So let's move on. Let's start from decimal structure. In the previous videos on mental models of numbers, especially part 2, part 3, I presented a vision where a decimal number, for example this one, is actually interpreted as this complex of components. So here each symbol Ji1, I capital and J capital represent a position. This is a positional symbols. These positional symbols can be multiplied. So we have a table of multiplication rules for these positional symbols. And multiplication is like this. If we multiply 1 by 1, it's clearly 1. But if we multiply I, that represent 10, we multiply it by, let's say, capital I, that represent 1/10, we will get 1 again. So this is the multiplication rules that we get for these positional symbols. And in addition to this view, or this view perspective, we also need to interpret the rule that when position overflows, we carry that overflow to the next position, right? So that rule is expressed in this form. If we add 10 times 1s, like shown here, we get I. I is in next position. If we add i's 10 times, we get j. J is in next position to the left. And similarly on the right hand side of the digital dot, positional symbols added like this. 10 times uppercase I gives 1. 10 times uppercase J will give us capital I, and so on. So these are just standard numbers, positional numbers with digital dot. And this is kind of an underlying structure for these numbers. Now, using these complexes that I am circling, these complexes, we can multiply them, we can add them like polynomials. We can open parentheses and use distributional law, use multiplication table and addition rules, and we get our just decimals, operation on decimals. So this is considered in great details in mental model of numbers, part 2, part 3. And let's now consider connection to common fractions. Common fractions on the other side are objects like 1/3, 1/5, 7/9, or also I can add here just natural numbers 3, 5, or 173, doesn't matter. So all these numbers are objects in this space, and we have special multiplication operations that I also noted here, some of them, like n multiplied by 1/n is equal 1. And we have a special addition rule, like we use common denominator as an addition rule. And now we need to answer the question, what is the value of 1/4? What does it mean? What does it mean to compute 1/4? And I want to look at this from perspective of a mapping. So there is actually no such thing as a value of 1/4. That's wrong abstraction. So what really happens is that we have a space of decimals that we just described. Decimals. Here we have operation of addition, operation of multiplication. We have special symbols like J, I, 1, I, J. There's can be infinite number of these symbols, but this is not the point. So we have these special symbols, and we have special objects here, like linear combinations of these symbols, sum of so here we have one space. On the other side we have a space of fractions, common fractions, or just fractions. This space is full of numbers like these objects, and it also has its own rules of addition and multiplication. So when we ask a question, what is the value of 1/4? 1/4 here. What we really care about is mapping. So we want to have some mapping that will bring all our objects from fraction space to decimal space. So value of 1/4 or compute 1/4 means actually find an object here. Find some representation here that will behave similarly to 1/4 on this side. So on this side we know that 1/4 multiplied by 4 equal to 1. So we want to find these pairs. We want to find 4 here, like some object, and we want to find 1/4 as an object, and we want to find them such that, let's say, A here and B here. We want to find them such that A multiplied by B will be equal to 1. Okay, so and what kind of A and B? A and B is like alpha I plus beta J plus gamma plus AI plus BJ. So this is the form of objects that that live in decimal space. Okay, so we want to find this mapping. So the value or the computation of 1/4 is just the representation of the similar object in another space. We could ask similar exact question like, what is the value of 0.25? What's the value of 0.25? And by that we would mean that we actually care about the mapping from decimals to fractions. And we would say that value of 0.25 is 1/4. These are symmetrical situations, and there is no computation per se. They're just representation of the same structures, of the same set of objects and operations in different spaces. Sometimes representation is a problem. For example, if we have 1/3, we know its special representation here. It will be 0.33 and infinite series of 3's that we represent as 3 in parentheses. But these parentheses actually introduce new axioms. So it alters these rules that we considered from addition and multiplication and all these positional symbols. So in short, that's not the topic of this video, but in short, when we talk about something in parentheses, it means that we switch from 10 digits system to 9 digit system, because basically this is equivalent or the same as this is. So we have like 0.999 and 9 is the same as 1.000 and etc. and 0. So we can interpret this as a change of axioms, or these axioms, from base 10 to base 9. Okay, so this is the correspondence between decimals and fractions. Now let's introduce dual decimals. So when we consider the rules for positional symbols like I multiplied by I equal j multiplied by j, these are the rules of multiplication. They are symmetric. These rules are symmetric, so when we multiply I by I we will get j, but similar will happen for capital I's that denote positions on the right hand side of dot. I multiplied by I will equal to j. But what happened with addition is that we had 1 plus 1 plus 10 times, and we agreed that this will be equal to I. So I is position on the left of ones. So this rule that when we overflow a position, let's say 7 plus 6, we overflow, we put that new number to the left position, right? That's a break of symmetry. I want to consider a case where 1 plus 1 plus etc. 10 times actually equal I. So to restore the symmetry, right, we need to consider the opposite rule. So in this case, 6 plus 7 plus 6 will be 13, but we carry over to the right. So it will be 3 here, but 1 here on the right. And this is exactly the same symmetry as we had with fractions and two operations, plus and plus. So here we can just mark that this rule corresponds to this plus, this is just standard plus, and this symmetric rules corresponds to this plus, okay? So if we base our system on this type of rules, let's say we already have this one rule. If we add I plus I plus I 10 times, so carrying over to the left would mean that we get to the position j. And if we add, for example, i's 10 times, we will get 1. Remember that here we have our dual plus operation. So with these rules, we can now consider dual decimals. So let's play a little bit with these dual decimals. Here is a table, and we will have quantities, different quantities. Their representation as fraction, as common fraction in the second column. Their representation in terms of our standard decimals, and now we will find out how to represent them in our dual decimals. So the easiest case here is probably one. Let's start from this 1/2, this one. So 1/2 is just, so I want to mention, to differentiate two decimal notations. One is for standard decimal, another is for dual decimal. I will use notation dot with a hat on top. So for example, 35.72. That's decimal in standard notation. Dual decimal will be look like 35 dot with hat on the bottom, 72. So this is my notation. And now let's consider this first 1/2 case. So 1/2 represented as 0.5. That's clear. Now, what is the dual decimal representation? So let's recall that 1/2 is 1 plus 1. Okay, so we have, for position representing ones, we have 2 of such position. So we have 2. And then I put it here, the dot here, with an arrow down, and I put 0. So ones for standard decimals stay on the left of dot, right? Here is 2. For example, here it's 2 ones, right? So in case of decimals, my designation will be 0.2. This means 2 ones in dual decimal notation. Okay, this is why 1/2 represented by 0.2. How is represented 1/3? 1/3 in standard decimals represented with this problematic infinite notation, like infinite number of 3's here. In our case, 1/3 is 1 plus 1 plus 1. So it's just 3 in the position of units. So this is just finite 0.3 notation. Now it's time to move on probably to this example where we want to represent 2. 2 represented in decimal notation as 2.0. I'm putting dot and 0 here just to differentiate between fraction and decimal representation. Notice here something interesting. So when we represent 2, it's very similar to 2. 2 and 2 here and here. When we represent 1/2, suddenly we get 0.5. That's interesting change, unexpected turn of events. So when we represent 2 in dual decimal case, how we can get 2 actually? 2 is the same as in terms of tens, right? Because our system is decimal based on 10. So 2 in terms of tens is just 10 added 5 times. So where is our 10 digit stay? 10th digit. It's just on the left of our dot. Okay, so 10 times position is, 5 times position is 10th, so we put 5 here on the left of the dot. So 2 is actually 5. And how come 2 can be 5? Same way as 1/2 is 0.5. Okay, so 2 represented by 5. Let's check what is representation for 3. Same rational, 3 is very close to 10 plus 10 plus 10, but it's not 10 plus 10 plus 10, which is 10 over 3. We could take 100ths and sum them 33 times, and we would get 100 divided by 33, which is closer to 3 but still not the 3. So we end up with something similar to infinite 3's after the dot, but instead of that we have 3's before the dot. This is representation for number 3. And now let's move on to this example. What's representation for 10? 10 is 10 for standard decimals. For our dual decimals, 10 is 1. Okay, that's 10. Now let's represent the final one, 1 over 25. 1 over 25 is 0.04 in decimals. And let's consider this a little bit closer. So let's move on to new page. 1 over 25 is the same, let me just write it, equal to 1 plus 1 plus, and many times, exactly it's 25 times plus 1. So there is 10 times and another 10 times and then 5 times, right? So this is 5 tenths, 5 of, sorry, 2 of 1 plus 10 times and plus 1 plus 5 times. Okay, so we know from our addition rule that this will be equal to capital I. Right? So, this is just ones. So position of ones is here, so we put 5. Position of I is here, so we put 2 here. And here is 0 for consistency of notation. So 1 over 25 is represented in our dual decimals as 0.52. Let's put it in here, 0.52. Okay, let's try something different. Let's practice a little bit with this notation. 2.7. What is this? It's 2/10, right? 10 plus 10 and plus 7 ones. 1 plus 1 7 times. So this is, we need to consider this as 10 over 1 plus 10 over 1 plus 10 over 10 7 times, right? 7 times. So we use the rule of common numerator, so we get 10 over 72. And let's rewrite it as 1 over 7.2. And 1 over 7.2 in turn is equal, I have a computation here, is 0. In a standard decimal notation, 13888 and infinite number of 8s. Okay, so this is standard decimals, and this is the same value represented in dual decimals. We see here something interesting. So here 1 over 7.2. It looks like very similar to 2.7 but in reverse. So let's try and play the game in opposite direction. Okay, so let's say we have 0.2, 0.4 in standard decimal notation. It's the same as 1 over 2.5, correct? So now let's play this reverse game. Let's map this value to 5.2. And here is still decimal notation. And I should put here is also decimal notation. So 5.2 in dual decimal notation. Let's see, what is this? This is equal to 5 times adding 10 plus 1 and plus 1. Let's compute what is this. This is equal to 10 over 5 plus 1/2. Let's compute what is this. It's 2 plus 1/2. Rule of common numerator. So we have 2 over 1 plus 2 over 4. It's equal to 2 over 5, which is 0.4. So it looks like this is true, that this type of reverse and inverse is a way to convert dual decimal notation into standard decimal notation. Let's do a little bit of practice. Let's use these addition rules and try to compute some values. For example, we have 2 resistors with 10 ohms each, and we remember that our dual addition operation can find the total resistance as R total equal 10 plus 10. Let's compute this in terms of decimals, our dual decimals. So 10, value or quantity 10, in our dual decimals expressed as 1, 0. Okay. When we sum 2 decimals, let's use sum like this, 1. We should use very similar rule, but we start from left and move on to the right instead of from the right to the left. And when overflow happens, we carry over to the right position instead of left position. In this case, we just have 2, 0. That's dual decimal. Now we need to convert it to just fractions, normal fractions. What is 2? It's the same as 10 plus 10, which is 5. So fraction 5 represented in decimals, in dual decimals, as 2. Okay, so we got 5 as a result. So, and we know that 5 is also the result of total resistance. So we made computations through decimal representations here. Let's consider another example. Let's take more interesting case. 25 and 25. So first we need to convert 25 to decimal representation, dual decimal representation. What is dual decimal for 25? Let's notice that 100 added 4 times will be equal to 25. So what we have 40 dot 0. That's decimal representation for 25. Okay, now we sum both. With our dual operation. We get 8 is 0 dot 0. So how to convert back? 8 is what? It's 8 times 100. This is the same as 100 divided by 8, and this is the same as 12.5 in standard decimal. And we know that total value will be 25 plus 25 equal 12.5. So we have a correspondence here. Let's consider final example with 20s. We have 20 here and 20 here. Let me check. Is this visible? Yeah, it's okay. So 20. What is 20 in our dual digital form? In dual decimals form? 20 is 5 times added 100. So it's 50. Now let's add 50 and 50. Plus. So we start from the left, we don't start from the... 5 plus 5 is 10. 0 remains. 1, instead of carrying over to the left, we carry over to the right. We get 1 here, and we get 0. So we got 1, 0. This is equivalent of just 10, right? That's digital, dual, decimal representation for 10. And we know that our total for our case will be 20 plus 20 equal 10. So we can compute using decimals. We can mimic operations on fractions, but we use dual decimals for dual addition operation. Okay, very final example. It will be, let me just delete everything here. Not everything, but I need some space. So let's have 1/3 here and 1/7 here. So 1/3 represented in our decimal form as 0.3 and 1/7 is 0.7. So let's sum these two. 0.3 plus 0.7. 0 plus 0, 0. 7 plus 3 is 10. Carry over to the left, so it's 0, 1. So this is equivalent to, so this is ones, these are 1/10. So this is the same as 1/10. And we know that our total in this final case will be 1/3 plus 1/7. It will be equal to 1/10. So we see that operations on decimals equivalent to operations of fractions. And I think we can make some conclusions here. This is final slide of this video. What we made, we took our dual addition operation that we use for fractions, and we based on it, we introduced decimals, decimal numbers, decimal fractions. Those decimal fractions are better suited to represent fractions, but they are not as good for representing numbers larger than 1. So we showed how to represent, how to perform operations column-wise, how to add digits and how to do carry over to the right instead of to the left. We showed how to convert fractions to dual decimals and compared that to conversion from fractions to standard decimals, and we showed a rule how to convert dual decimals to decimals and vice versa. And we demonstrated equivalence, so operations of addition, for example, performed on dual decimals is equivalent to operation of addition performed on common fractions. That's it for today. Thanks for your attention. This was Alexander on Math Musings channel. Please subscribe.